Okay, so in this video, we're going to cover an important property of Fourier series, which is called Parseval's theorem. Okay, so this is Parseval's theorem for Fourier series. It turns out there's also going to be a Parseval's theorem when we get to Fourier transform. Okay, so that's why this one is for Fourier series, but we'll get there when we get there. Okay, so what's the setup for a Fourier series? As we all know, we have to have a periodic function. Okay, with period t. Okay, so if f is periodic with period t, and I'm going to use this notation that f of t double arrow f sub n, that means f of t has Fourier series coefficients given by the f sub n's. Okay, then what do we get? Well, we get this. Okay, this is Parseval's theorem, and I'll write it down and then I'll kind of explain sort of where it kind of comes from. Okay. All right. So then this statement is true. Okay, this is Parseval's theorem. Now, what's special about this? Well, there are a few things special, and we'll kind of talk about some of them. But first of all, notice on the left here, we have an operation on the time signal, f of t, right? What do? We take its magnitude squared. Okay, f of t can be complex, so we have the magnitude there squared. And we integrate it over a period and divide by the length of that period. So this is the average value over a period of the magnitude squared of f of t. That's what the left side is doing, calculating. What about the right side? Look at the right side. It has the Fourier series coefficient on the right side. Okay, that's pretty cool that it can relate the signal in time to another operation involving just the Fourier series coefficients. Okay, so now how can we sort of interpret this left side? Well, yeah, at least here's the inspiration. If you have like a voltage in a circuit and you like a voltage signal and that voltage is going through a resistor, and you ask how much power is dissipated in that resistor, then the equation for that is going to be V squared over R. That's the power. Okay, dissipated in that resistor. And so if we think of this voltage as sort of being our f of t, and we let this R be a 1 ohm resistor, then we get that the power dissipated is f of t squared. Okay, now we want to be able to deal with complex valued f of t, and that's why we have these complex magnitude bars here. Okay, because for real numbers, whether I square it, whether I square a real number before or after putting absolute value bars makes no difference, but for complex numbers, it does. If I have a complex number and I square it, that is very different than the magnitude squared. Okay, so anyway, this is sort of the inspiration. You can read more in the book about it if you want. They pretty much just say this behind what's happening here. And that's why we have sort of a name for this. And it turns out it's the average power dissipated, or sorry, the average power of the signal over a period. Okay, so this is sort of like the instantaneous power, sort of taking inspiration from this idea. Okay, but obviously adapting it a little bit. And then we're going to integrate that over a period and divide by the length of the period. In other words, take the average value of this power over a period. So the left side is sometimes referred to as the average power of the signal. I'm going to erase this for now. That was just sort of a high level sort of way that maybe you can remember it a little better. So the left side is sometimes called the average power of the signal. Okay. And the right side, what's it saying? It's saying you can take the average power of your signal and it actually splits up into a sum of all of these terms involving each Fourier series coefficient. And so sometimes these terms here are called the power spectrum. Okay, these terms you don't really need to know for this course, just thought I'd tell you in case you ever see them again. Okay, and what it's saying is that you can take the average power of your signal over a period and actually see which Fourier series components, sort of which frequency components that power is split up into, right? So maybe, f sub n for a certain n has sort of more of the power contained in that frequency component than another one. And we'll see more of this when we get to Parseval's theorem for Fourier transform too. But anyway, this is sort of just an overview for now. And this is the property that is true. And it's very powerful, actually. We're going to prove a pretty cool thing with it today. But first, let's actually prove that this is true. So let's prove this. Okay, it's not too bad. So we'll start with the left side. Okay, we'll start with the left side. Now what can we do? Well, we're going to take that magnitude squared, and we're going to split it up into f of t times f of t conjugate. Okay, we know that the magnitude squared, this is in the complex numbers review video, magnitude squared of a complex number is just that number times that number conjugate. Okay, that's a property of all complex numbers, so we're using that now. Now what can we do? Well, now we know that f of t has a Fourier series, so let's plug in, but let's plug in for this one that we conjugated. E to the jn omega naught t conjugate dt. Okay, now we'll bring that conjugate inside because the conjugate of a sum is just the sum of the conjugates. Okay, and we get the sum of f sub n conjugate, and then e, what happens when I conjugate this? I just negate the j and the exponent. All right, now what can we do? Well, some of those terms in there don't depend on t anymore, so I'll bring them out. I'll bring the sum outside. Okay, I'll bring the fn conjugate outside. That doesn't depend on little t that we're integrating. Okay, and then what do I have left? I have 1 over t integral over a period of f of t e to the negative j n omega naught t dt. Okay, and now is any part of this equation familiar? Well, at least one part should be. All right, what is this? We've seen this before. That's just our formula for the Fourier series coefficients. Pretty cool. Okay, so this whole thing just simplifies to f sub n conjugate times f sub n. And then, of course, using that same property of complex numbers we talked about above, let me maybe just shrink all of this a tad bit, give myself a little more room. Okay, then we have a complex number conjugated times itself. That's exactly what I have here. And so we get the magnitude of f sub n squared. Okay, so there you go. That's Parseval's. This side equals this side. All right, so it's a really useful property because sometimes integrals can be easy to compute, but this sum could be hard to compute. We're going to see an example of that right now, or vice versa. Sometimes this integral can be hard to compute, but these sums can be easy to compute. Okay, and so based on which side is easier or harder, you can use Parseval sort of as a bridge to go between them. So it's a very useful property. So let's see an example. Okay, and for this example, I'm going to draw a function here that should look pretty familiar. Okay, so I'm going to call it f of t, and it's going to be the sawtooth function. And we saw not quite this one, as you'll see in a second. I'll just draw 3. We saw a very similar one in a previous video. Oops. The previous one we saw had 1s there, but this one is going to have 2 pi. And there's a reason for this. Of course, it repeats. Okay, so we can see here that the period, of course, is 2 pi. And so omega naught is 2 pi over the period, which is just 1. Okay, and what we want to do is we want to use Parseval's applied to this function, and you'll see we get a cool result. Okay, so first of all, we need the Fourier series coefficients, right? That's part of Parseval's. So we could do all the calculation again, but let's use our calculation from a previous video and some of the properties we learned. Okay, so from a previous video, we found the Fourier series coefficients of a different function that I'll call g of t. Okay, it was also this sawtooth function, but it had height 1. So I remember this from a previous video. Okay, so we had that function before, and the Fourier series coefficients of those, or of that function, were that the 0th one, which I'll call g0, because this function I called g of t, was a half. We figured that out. And then for all the other ones, when n wasn't 0, it was 1 over negative j 2 pi n. Okay, so if those are the Fourier series coefficients of this function, how can we get the Fourier series coefficients of this function? Well, we can just see how g of t is transformed into f of t. So what do we have to do? First of all, we have to multiply the amplitude by 2 pi, right? So we have to multiply the amplitude by 2 pi, okay? And then we also have to do a time scale, right? Here, that 1 value, this g of t is period 1, I want to scale it, I want to expand it, so that now that 1 value is pushed to 2 pi. So how do those operations affect the Fourier series coefficients? Well, we looked at both of those properties in the Fourier series properties video. Okay, and when you scale things by 2 pi, the coefficients just scale as well. It's really simple. Okay, so when you scale things by 2 pi, the coefficients scale as well. We want f sub 0 and f sub n. Okay, we want the Fourier series coefficients of f. And what happens when you time scale? Well, when you time scale, it was kind of a strange thing, but it turned out the Fourier series coefficients didn't change at all. Okay, the Fourier series coefficients actually stayed the same when you time scale. The thing that changed was the period and the fundamental frequency. So in the Fourier series, which I don't have written, I'll just write it real quick to remind you. In the Fourier series, when I time scale, this thing changed, the omega naught changed, but these f sub n's actually didn't change at all. Okay, and you can review the properties video if you forgot about that. Okay, but so to sum it up, when we have to scale the amplitude by 2 pi, that'll make our Fourier series coefficients scale by 2 pi. And when we scale the time axis, they actually won't change. So all in all, f sub 0 is just going to be g sub 0 times 2 pi. And f sub n is going to be g sub n times 2 pi. So it's pretty simple. So 2 pi times a half is just pi. And 2 pi times this, you can see it cancels the 2 pi in the denominator. I get 1 over negative jn. All right, so now we have our function f of t, we have its Fourier series coefficients, and now let's apply Parseval. So now let's use Parseval's theorem on f of t. Okay, and what does it say? Well, on the left side, I have 1 over the period times the integral over a period of the magnitude squared. So what's the period here? Well, it's 2 pi. So I'm going to get 1 over 2 pi times the integral over a period. Let's choose 0 to 2 pi. That looks like a nice interval to choose. So 0 to 2 pi of the magnitude of f of t squared, dt. And that's going to equal, what does it equal? It equals the sum of the magnitude squared of all the Fourier series coefficients. Sum of the magnitude squared of all the Fourier series coefficients. Okay, so now let's go down the left side. Let's see what the left side equals, and then we'll see what the right side equals, and then we'll make a conclusion. Okay, so what is going on the left side? Well, I have a 1 over 2 pi. I have an integral from 0 to 2 pi. Now, what is the magnitude of f of t squared when t is between 0 and 2 pi? Well, we have it right here. When t is between 0 and 2 pi, f of t just equals t. Right? F of t just equals t there. Okay. And so what's the magnitude squared of t? Well, t is a real number, so the magnitude squared is just t squared. And now we can do this integral just fine. It's 1 over 2 pi times t cubed over 3 from 0 to 2 pi. And what is that? Well, when I plug in 2 pi, I get 2 pi cubed on the top, but one of those cancels. So 2 pi squared, which is 4 pi squared, divided by 3. And when I plug in 0, obviously I just get 0. Okay, so that's the left side. What about the right side? what is the sum of all the Fourier series coefficient magnitude squared? Well, we see that f sub 0 is kind of different from the rest, so let's take that out. So we'll consider when n is 0, what's the magnitude of f sub 0 squared? Well, it's just pi squared. Now we have the sum of all the rest. So n is not 0. Of the magnitude squared, well, what is the magnitude of this Fourier series coefficient? Well, it's just the magnitude of the top over the magnitude of the bottom. Magnitude of the top is 1. Magnitude of the bottom, well, the magnitude of negative j is just 1. And the magnitude of n is going to be the absolute value of n, but you can see then we square it. So all in all we get is 1 over n squared. All right, that's the magnitude squared of that function. It's 1 over the magnitude of n squared, but n is a real number, so magnitude of n squared is just n squared. If n is negative, negative n squared is still n squared. Okay. All right, so that magnitude squared is just 1 over n squared. And now what can we do? Well, we'll keep the pi squared the same. And now you can see, wait a second, whether n is positive or negative here doesn't really matter. Right? It's an even function of n. So the sum, I go over first the negative ends and the positive ends, but I'm really just summing up the same thing, whether I'm going over the positive ends or the negative ends. So this is really just twice what I get going over either one of them, so I'll pick the positive ones. 1 over n squared. Yeah, I just took the sum, broke it up. The sum over the positive ends and the sum over the negative ends is the same. So I'm just going to write 2 times one of them. All right, so what does that tell us? That tells us that if I subtract this pi squared from the left side, right? Because if we follow this equals all the way around, we get this equals this. So let's subtract pi squared from both sides, and we'll get pi squared over 3, right? 4/3 minus 1 is 1/3, equals 2 times this sum, n equals 1 to infinity of 1 over n squared. And that implies actually a really famous result, believe it or not. Oops. That if I have the sum from n equals 1 to infinity of 1 over n squared, I actually get pi squared over 6. Pretty crazy result. I mean, this left side, if we just expand this, when n is 1, we get 1 over 1 squared, which is 1. And then when n is 2, we get a 4th, and then 3 and 9th, 16th, so on. Somehow this sum actually equals pi squared over 6. I mean, where does pi come from? Right? It's really cool, really bizarre. This is a famous result. Euler, the same Euler from, we use Euler's formula. He actually proved this in the 1700s. So it's a very old result, but pretty cool that you can get it using Fourier series and Parseval's theorem. Okay, so anyway, that was an example. So hopefully maybe Parseval's makes a little more sense now, and we got a cool result out of it. So that's all I had for this video, and I will see you in the next one.